Okay, welcome everybody. It's my pleasure to be here and to talk to you about graph algorithms and graph data structures. This will be a talk that will probably include mostly topics accessible to top-coder algorithm track division 2 participants, with maybe a bit of harder stuff here and there. And I'll be talking about a few of my favorite problems, algorithms, and such, and try to give you a little bit of background, how I think about graph problems and how you can approach them when solving them. So the whole, the main topic of the webinar today are graphs, and these are not graphs of functions, but these are graphs in the discrete sense. So we have a collection of vertices, we have a collection of edges that connect those vertices, and usually we are trying to use graphs like this as tools. We are trying to use them in order to model situations from real life that we are trying to solve. And it turns out that many of the problems you can encounter in real life can be modeled using graphs, and you can think about graph algorithms when trying to solve those problems. So there are some very natural settings where you can talk about vertices and edges in the graphs, for example, shortest path problems. So everybody uses Google Maps or some similar software on a day-to-day basis. You are trying to look for the fastest way of getting from A to B. And in this setting, the graph is very natural. So the vertices are simply the locations where something interesting happens, for example, crossroads or a place where there is a bus station or something like that. And the edges represent elementary steps of travel, for example, a connection between two adjacent bus stops or a street, and so on. And the real life question, what is the fastest way of getting from point A to point B within the city, can then be represented as a graph question within this graph. What is the shortest path from one vertex to another? But many other situations can also be modeled using graphs. For example, on Facebook or different social networks, you have friends, and those friends have other friends, and between those friends, we have a bunch of connections. And this can also be represented as a special type of a graph. Each of the vertices is now one of the people who are using the social network. Each of the edges represents one friendship. In some social networks, friendship is mutual, which we can model using undirected edges. In other social networks, the friendship is one directional. You follow somebody, and this can be represented using directed edges. This person is following that person, but the other person doesn't necessarily care about the first one. So there are various types and flavors of graphs, and we have to always think about selecting the most appropriate one when modeling our situation. So sometimes we will have graphs in which each vertex has some property, a color, a weight, or something like that. Sometimes we will have graphs where edges have properties and so on. And the very first step of being able to solve problems using graphs is choosing a good representation of the graph in memory. And there are two very famous basic ways of storing graphs. One of them is an adjacency matrix. The other one are adjacency lists. Let's just run through both of them very quickly. So if we have a graph like this, with, let's say, 4 vertices, 0, 1, 2, 3, and several edges like this, the most straightforward way of representing such a graph is representing it using a two-dimensional table, a matrix, where we have a row for each of the vertices, we have a column for each of the vertices. The diagonal of the matrix corresponds to self loops in the graph. Sometimes it makes sense to have a self loop in a graph, but sometimes it doesn't. Again, it depends on the problem we are trying to model. And if we are storing just a simple graph, what we can do now is in each cell of the table. So this is a cell that has coordinates 0 and 2, and it's telling us about the edge between the vertices 0 and 2. If the graph is undirected, the table is symmetric. If the graph is directed, we can have the row number be the vertex from which you are going with an edge, and the column you have the vertex where you are pointing it. So for example, if we had a directed graph, all of these are pointing into the vertex 3, and the remaining edge is pointing from 1 to 2. You could now have stored it as follows. So there is an edge from 1 to 2, and there is an edge from 0 to 3, from 1 to 3, from 2 to 3, and all of the others are not in our graph. The main advantage of such a way of storing a graph is that it's that simple to process. In constant time, we can take any pair of vertices and examine the cell in the table to be able to tell whether or not these two vertices are connected by an edge. The disadvantage of such a way of storing graphs is that the size of the table is not necessarily proportional to the size of the graph itself. For example, here in this table, we can see that there is a large cluster of zeros below the diagonal because we don't have any of those edges. And we are just wasting space storing those zeros. And this is a question whether or not we can afford doing it. So it's not directly correct. It's not always correct to say that you shouldn't use adjacency matrices to represent graphs because they are inefficient. You can absolutely use them, especially if your graphs are small and or if your graphs are dense. If you have very, very many edges, for example, if you have 1,000 vertices and 100,000 edges, then by all means use the adjacency matrix because you cannot do significantly better than that. And if your graphs have 50 vertices, then use whatever you like because it doesn't matter. Use whatever is the most convenient and you can get away with it. But if you are running a social network with 1 billion users, and each of those 1 billion users has several hundreds of friends, there's a very, very big difference between just storing information about the friends of each person, which is manageable, and you can do it on a normal computer or on a cluster of computers, and storing a two-dimensional table that has 1 billion rows and 1 billion columns, which would require vast amounts of space, and most of this space would be wasted. So in practice, if we are storing large graphs, we are usually choosing a different representation. And the other option we have is to store the graph as a list of lists, or more precisely, in any normal programming languages, you would use an array of arrays of variable lengths. So we, for example, in C++, a vector of vectors and not so using actual lists that allocate each of the nodes separately just to store a graph is usually an overkill because it's not cache friendly and you are just making your code unnecessarily more complicated. So the easiest way is just to have an array for each of the vertices. And what it looks like is for each of the vertices 0, 1, 2, and 3, you will have one array that will contain all of the neighbors of this particular vertex. So again, if this is an undirected graph, it's simply a list of neighbors. If it is a directed graph, you can view it as a list of, for example, outgoing edges. So what we would have in our case is we would have information stored like this. So for vertex 0, there is only one outgoing edge, and the edge is pointing to vertex 3. So for vertex 1, there are two different outgoing edges. One of them leads to vertex 3, the other one leads to vertex 2. The advantage of this representation of graphs is obvious that you can essentially in all graph algorithms, one of the basic operations we want to do is we want to examine all of the neighbors of a vertex we are currently processing. If you are storing the neighborhood of the vertex in this way, so you are just storing the actual neighbors, then you can traverse the neighbors in the time proportional to the number of those neighbors. in the previous example, if you are using an adjacency matrix, you need to traverse the entire row of the matrix. You will encounter many zeros saying this one is not connected directly. And sometimes you will encounter one that will tell you, yes, this is a neighbor. So in that case, you are wasting some time looking at vertices that are not immediately adjacent to this one. In the adjacency list technique, you are able to generate the neighborhood efficiently. On the other hand, there is a disadvantage, and the disadvantage is that you cannot easily tell whether or not two vertices are connected by an edge. If I have the question whether vertices 1 and 2 are connected, whether there is an edge from 1 to 2 in the directed graph, the only way I currently have to answer this question is to look at the list for vertex 1 and examine everything in the list until I either discover the value 2 or reach the end of the list. And there is, of course, a third solution that can be like the best of both worlds, and sometimes in practice, especially if you are processing large data sets, you can go for a compromise between those two. And the compromise is that instead of having just an ordinary vector of values here, you can replace it with a hash set. Hash sets are something that is available in all modern programming languages for free, so you have them in standard libraries. And if you are storing the graph in this way, so for each vertex, you are storing a hash set of its neighbors, now you can do all of the operations efficiently. You can both check for the presence of an edge. So if you are looking for the edge 1, 2, what you do is you look into the hash set for vertex 1, and in expected constant time, you query whether the value 2 is present in the hash set. And you can also iterate over the values stored in the hash set when you want to traverse all of the neighbors of a vertex. So in comparison to a vector, this introduces some extra overhead, both in terms of time and in terms of memory, but this is just a constant factor in both cases, both worlds. It's not exactly the one recommended technique for programming competitions because of the constant factor that can sometimes matter. But for many real-life applications, this is the way you want to do it. If you want to, and especially if your graph changes in time. So if your graph isn't static, if your vertices or edges can appear and disappear, the implementation using hash sets is much more flexible than an implementation using vectors, when you always have to locate the place where the edge is stored, then remove it from there, then shift everything to make it work in memory. So hash sets are a very powerful tool, and hash maps as well, and learning to use them properly is an important step in every programmer's education, in my opinion. All right, so that being said, let's talk about some graph algorithms. And we will start with a graph algorithm that is very, very simple. And most of you will have heard about it and probably also implemented it once or twice. And this is a graph algorithm, a graph traversal algorithm called depth first search. Or usually we just write Dfs. Dfs is an algorithm that explores a graph in a way in which a single person would explore an unknown city. So if you are just alone in an unknown city, you cannot split into multiple groups and explore multiple regions of the city at the same time. All you can do is walk along the city and maybe try to have some marks that will tell you which places you already visited and which ones you didn't visit yet. So the most straightforward implementation of a DFS looks as follows. So DFS is best implemented as a recursive function. And sometimes it can be implemented just by having a single argument, the vertex we are currently trying to visit. So the first thing we do when we try to visit V is we will mark V as visited. And then one after another, for each neighbor of V, let's call it W. For each vertex W in the neighbors of vertex V, you call the recursive function Dfs for the vertex W. So what this means is that you are exploring the city from some location, and you will, if there are 3 different roads leading from this location, you will start by going along the first road. You will explore everything in the city that was reachable from that new location, and then you will return back, because each time this recursive call returns back from exploring some part of the graph, you are back again where you were, and now you can try a different street from the same location. So what this looks like on an example graph. Suppose we have something like this. So this is maybe the vertex where we are starting, and there is a bunch more of vertices in the graph. So we can have a graph that looks like this. This is where we started, so we mark the vertex as visited, and now we are trying to go over all of the neighbors of this vertex. So for example, first this one, then this one, then this one, and for each of them we will do the same procedure. So the person who started here is now going along this edge into the vertex, and from here we do exactly the same procedure. So first we mark the vertex as visited, and then we choose one of the neighbors and go there. We mark it as visited, we choose one of the neighbors and we go there. And one of the important steps of the implementation I actually forgot to list when I was listing the outline of the algorithm was what happens in the next step. In the next step, what happens is we are currently in this vertex, which I circled blue. We try to go along this edge, but we see that the vertex there was already visited. So the thing that was missing from my implementation was if you encounter a visited vertex, you don't go there again. This is something that was already explored. You just return immediately from the call. So at the very beginning of the Dfs function, you just insert another line saying, if you already were in this vertex, it is already marked as visited, just return back. So we will return back from there. We'll also check that this edge has already been visited. So this finishes processing this vertex. There is nothing new in the city we can reach from it. And now the Dfs returns. For the first time, we return to this vertex. We discover that there is nothing more to process. We return from there to this vertex. And now we still have an option to go along this edge into another vertex, and so on. Now we return back, and we return back to where we started. And at this moment in time, our Dfs has already visited the entire part of the graph that was reachable from the starting vertex via the first edge we chose. And now we do the same for the rest of the graph. So we will go here and visit a new vertex, and here, and visit the new vertex, and here, visit the new vertex, here, discover that the vertex was already visited. So retrace our path, and eventually the algorithm will terminate and visit everything that could have been visited. So in the very simplest form, in the way I introduced it here, Dfs is an algorithm that can be used to construct connected components of undirected graphs. If you have a graph that is connected, regardless of where you start in the graph, if you run Dfs from any of its vertices, it's easy to show that eventually Dfs will visit the entire component. Each of the vertices will eventually be visited by the procedure. This is why it's called the graph traversal algorithm. It's an algorithm that is able to visit all of the vertices within the connected components. So if you have a graph that consists of multiple connected components, you can run Dfs from one of its vertices, and it will color as visited everything in the connected component that contains this vertex, and then you can do it from another vertex that hasn't been colored before, and so on, until you have everything divided into connected components. But this basic usage of Dfs is just the very beginning of the story of what this algorithm can do. And in fact, in terms of graph algorithms, Dfs is something like a Swiss Army knife. This is an algorithm that can do very, very many different things by subtle modifications of the algorithm. So let's see what other nice things we can do with the algorithm. One other thing that can be extracted from Dfs, and let's start with with basics. Let's start still with something very simple. What happens if you run Dfs on a directed graph? If you run Dfs on a directed graph, each time you are processing the neighbors of a vertex, you are only processing the edges that are going out of that particular vertex. So suppose we start somewhere here, and now the Dfs would run along this edge and try to visit everything that can be visited on that edge. Eventually it will terminate. It will visit all of these vertices that were reachable from there, and it's also this one. And then we will try also this edge, and we will see that there is nothing more that can be visited in this graph. You can note that the vertex on the left will remain unvisited. So you start Dfs from the vertex marked by the incoming arrow. It will only traverse the graph, the part of the graph that is reachable along the edges from the vertex where you started. The most straightforward application of Dfs on directed graphs is topological sort, topological ordering of the graph. What this means, one very useful metaphor, one very useful thing we can model using directed graphs are dependencies between packages. So imagine that you have a software package system, for example, a Linux distribution repository, and there are dependencies between those packages, and the dependencies have the form: if you want to install package A, you also need to install package B that is necessary for package A to work properly. So each of the directing edges is telling us, in order to install A, you first need to install B. And directly without any changes, Dfs is doing the computation of one possible proper installation order. So you start Dfs in the vertex you actually want to install. So this is the package we actually want to have. And now Dfs is going through the list of dependencies of this package. In order to install this package, I need to install this one. Can I do it? No, not yet. In order to install this package, I need to install this one. Can I do it? Yes, it doesn't have any dependencies. So I just install it, return back. Is this package already ready to be installed? Not yet, it has a second dependency. So first we install everything that depends on this package, and then after that installation is done, we return back and install a package like this. So if there are no cycles in the directed graph, or at least in the part of the directed graph that interests us, then we are able to find one possible installation order for those packages. And the other scenario is if there is a cycle in the dependencies, we will eventually discover it by returning back to a vertex where we already were. And that's still on the stack. So if we had a less lucky situation, so somebody messed up the dependencies between packages, or maybe it's a more complicated word where you don't have such simple dependencies only. So if you have a situation like this, that package A depends on package B depends on package C depends on D, and D depends on B again. What will happen is you will start processing A, then you will start processing B, then you will start processing C, then you will start processing D, and suddenly you came back to vertex B, which has already started to be processed, but hasn't been terminated yet, hasn't been installed yet. And whenever this happens, then you know that you just discovered a cycle, and therefore there is no single installation order in which you can install those packages one at a time that will be satisfying matching all of the dependencies we have. So DFS is on directed graphs is telling us how to order them from the bottom to the top. So the bottom vertices are the vertices that have no outgoing edges, though in terms of the packages metaphor, these represent packages that can directly be installed without any dependencies. And we want to create an order of all of those packages from the bottom to the top in such a way that whenever we are installing a package, all of the dependencies have already been met. So this is something you can get by running DFS on a directed graph. But you can get much more than that. So if you have a graph like this, clusters of vertices like the B, C, and D here that lie on the same cycle, or more precisely clusters of vertices such that between any two of them you can go from X to Y and also from Y to X. Each pair is mutually reachable, are called strongly connected components of a directed graph. And in each directed graph, we can uniquely always identify the strongly connected components. So all of the vertices of the graph can be in a unique way split into some such sets of vertices, such that each of the sets is maximal with this property, and within each set, each two vertices are mutually reachable. And this is giving us very useful and non-trivial structural information about the graph that can often be used to our advantage. For example, if you are computing the value of some function or whatever solution to some problem, it is often the case that whenever we have a strongly connected component, the answer for each of the vertices on the component is exactly the same. And identifying strongly connected components is a tool we can have in our repository of skills, and it can be used as a tool in solving some more advanced graph algorithm questions. And I will now just give you an outline of what is known as Kosarajus algorithm that is able to construct and identify these strongly connected components, and it is done again by some clever modification of the Dfs algorithm. I will not go into details of this one. I will go later into details of another similar application of DFS on undirected graphs. So for this one, I will stay on a slightly higher level just to give you an outline of what's going on. So imagine you have a graph like this. So sometimes there is an isolated vertex, sometimes there is maybe something like this. There can be a cycle, or there can be multiple cycles that are fused together. So for example, now, if you look at these vertices, and maybe we have another one here in the middle, like this. So now, here we have a cluster of 5 vertices. From each of them, you can go to each other of them, but not all 5 of them lie on the same cycle. So this is some general strongly connected component. There can be another vertex here, maybe a pair of vertices here. And from this one, you can have something like this, one more cycle elsewhere in the graph. And now you can meet from there and from here in the same vertex. So in this figure, we now have on the whiteboard each of the green circles represents one of the strongly connected components in this directed graph. And this is something we want to identify with this. So what we want to do is we want to label each of the vertices by the strongly connected component into which it belongs. So you can imagine it as giving each of the strongly connected components a different color. And what is the main idea of doing this? So imagine that you start within the graph somewhere. Maybe you start within one of the larger connected components and you run Dfs. What are the vertices that will eventually be reached by the Dfs that is run from this particular vertex? Well, everything within the strongly connected component itself is reachable from the vertex where you started. So this component will be certainly reached, all of the vertices in the component. And now we can imagine that we have a new graph that is like one level above the original one. So imagine that we are looking on the original graph, but from very far away, and you see each of the green circles as one of the vertices of the graph. So now you have not a graph with 15 or whatever was the original number of vertices, you just have 6 of them. And from this vertex, originally you could have multiple edges that go outside to other components, but it doesn't really matter. What it means is that from this green vertex, you have an edge that goes to this green vertex. And if you run Dfs on the directed acyclic graph that is now formed by the green vertices and edges between them, the Dfs will simply color all of the reachable green vertices. And in the original black graph, this means that the original Dfs will visit exactly all of the black vertices in all of those components. So all of these will be visited by the Dfs, this one will be visited by the Dfs, and nothing else. And there's even more. There's even more because what's going on there is that, of course, it's possible that, for example, you started the Dfs somewhere in this graph, in this component, you colored a bit of the component there, but then you took an edge that took you into a different green component. At this moment, during the algorithm, during the first phase of the algorithm, you have no idea what those green components actually are. This is just me drawing a picture, already knowing the situation. So you now traverse along this edge into this component. And the important property now is that as soon as you started processing the first vertex within this new strongly connected component, the processing, the Dfs call, will only terminate after it has visited everything that is reachable from this particular vertex. So what this means is that this entire green component will be visited, and every other green component that was reachable from this one will also be visited. And all of this will happen before this vertex is considered to be final and before we return along this edge back to the component where we started. So now what this means is that the last vertex in this connected component to be finished processing will be after this one has already been done, but before this one has already been done. Yeah, so let's take a look at the exact moments during the run of the Dfs when it happens that a vertex is already finished processing. When can this happen? So now the claim is that the only situation when this happens for the very first time, it has to be in one of these bottom components. It has to be in a strongly connected component that has no outgoing edges. Well, why is this the case? Well, we started somewhere, we colored some part of the graph, we have already visited some of the vertices, and we already know that a vertex in the middle connected component cannot be finished processing before everything that is reachable from this vertex has already been visited. And the bottom connected component is reachable from it. So eventually we will get to the bottom connected component. And as soon as we enter the bottom connected component for the first time, from this vertex where we entered the connected component, the strongly connected component on the bottom, from this vertex, what will now happen is the Dfs will visit exactly the entire bottom strongly connected component. All of its vertices will be finished processing. And after this happens, we will now return one step higher. Maybe from there, we will now go to another bottom strongly connected component. We will now visit all of its vertices and so on. So if you are looking at the DFS in the original graph, but you imagine that you already know the strongly connected components, that somebody has already painted all of those green circles, then what DFS produces is a topological order of all of those green circles. You don't know it yet, but you can construct them in a very clever way. You will be just simply, during this first round of the DFS, you will be storing the order in which you finished processing vertices. And now you know that in this order, the very first vertex you finish processing is a vertex in a bottom component. So now you have an order of all of the vertices in the original graph. And now you know that this one is in a bottom connected component. So what you can do is you can take the original graph. Come on, mouse, behave. And in the original graph, you can now reverse the directions of all of the edges. So instead of edges going from top to bottom, as we had it before in the picture, now we have edges going from bottom to top. And also all of the edges within the connected components themselves have been reversed. But this doesn't matter. This doesn't change. Reversing all of the edges doesn't change the strongly connected components. Why is this the case? Well, because if you had a way of getting from X to Y and a different way of getting from Y to back to X, once you reverse the direction of all edges, you can use the second one to go from X to Y and the first one to go from Y to X. You just go backwards against the flow of the edges of the original graph. So the big picture, once again, of Kosarajus algorithm is that you will start by running DFS from in the original graph. There is a technical detail that you have to restart it from a new vertex again until you visit all of the vertices in the entire graph, just like when you are doing normal connected components. And what you are storing is a single array of size n. For each vertex, as soon as it is finished processing, you put it into the array. And now, as I was saying, you know that the very first vertex in the array is a vertex that is in a bottom connected component, and the very last vertex in the array is a vertex that was originally in a top connected component. The very last vertex to finish processing has to be a vertex that is in one of these connected components. And now when we reverse the direction of those edges, what you can do is you can start a second DFS from this particular vertex. And now from a top component, you got a bottom component. So there is no way to leave it. And if you run DFS from this vertex, you'll just color this particular connected component. And this will color some of the vertices. So we will now, and the rest of the algorithm is just, you can go backwards to the list. And each time you see a vertex that hasn't been colored before, you know that this has to be a vertex that is now a representative of a bottom connected component. And you can construct the strongly connected component with this one by just running a simple DFS. So this is the first advanced example of using the DFS to do something clever with a directed graph. And we can do very similar things on undirected graphs. On undirected graphs, we have also more precise versions of connectivity. So in addition to talking about just simple connected components, we can look at situations where the graph is holding together, but only barely. So there is a single vertex or a single edge with the property that if you remove it, the graph will fall apart. The vertices with this property are called articulation points or cut vertices. The edges with this property are called bridges. So it can look like something like this. So for example, now the vertex circled in red is a cut vertex. If you remove this vertex from the graph and remove all of the adjacent edges to the vertex, you will get two separate connected components. This is one, this is the other. Or in general, if the graph is already disconnected, the usual definition of a cut vertex is generalized to say that the number of connected components increases if you remove such a vertex. And for example, this edge is a bridge. If you cut the edge, again, you will get two separate connected components. Previously, you could reach the left half from the right half and vice versa by traversing this edge, but this is the only way of getting between those two parts of the graph. And again, in general, what you can do in any undirected graph, if you knew all of the cut vertices and if you knew all of the bridges, so in this case, it looks like this. The red ones are the cut vertices and the bridges in this particular graph. The graph will now fall apart into several, let's call, well, there are still components. In this case, the proper name for them is two connected components, or sometimes for short, we call them blocks. And in this case, we are not dividing the vertices of the graph into these components. What we are doing is we are dividing edges of the graph into these components. So in this picture, each of the blue circles is one of the blocks. The block holds together, and even if you remove any single vertex, the block will still hold together. And if you remove any single edge, the block will still hold together, with the only exception of blocks that consist of just a single edge that change from one edge to nothing. And the question is, again, how to identify these particular spots in a graph. This can be, again, very useful in many different algorithms because, for example, if you have a bridge in a graph, you know that each and every possible way of reaching something on the left from something on the right has to go through this particular bridge. And sometimes you can split a big problem along the bridges and solve it only for separate blocks and so on. So now the question is, how can we identify all of the bridges in a graph? How can we tell whether or not an edge of a graph is a bridge? And once again, DFS is giving us a tool to do this. So here's how it works. We'll start by talking about one modification of DFS. And the modification is that each time you visit a new vertex for the very first time, what you can do is you can remember the edge you used to enter this particular vertex. If you run DFS on a connected graph, what you will get by this collection of edges will always be a tree, and this is called the Dfs tree of a graph. So this is the vertex where you started. From there you went to a first neighbor of this vertex, and so on. And for each vertex, you are storing the edge you used to enter this vertex for the very first time. And you can see that at any moment during the run of the algorithm, you have a tree, because at the beginning you have just the vertex where you started. And always, each time you are visiting a new vertex for the very first time, you are going from a vertex you already visited to a vertex that hasn't been visited before, which means that you have the tree that already exists, and you are adding an edge from an existing vertex on the tree to a vertex that is not on the Dfs tree. And now for the Dfs tree, what can we tell about the remaining edges of the graph? So we have a graph that originally had n vertices and m edges. M was at least n minus 1 because we said that the graph is connected. So n minus 1 of those edges form the Dfs tree. Where are the other edges? What can they look like? What directions can they have? Which vertices in this Dfs tree can they connect? And the answer is that this is quite severely restricted. So for example, you cannot have a the green edge or this green edge or this green edge in the graph. Why would this be the case? Why can we tell that the green edges cannot exist in our graph? Well, let's see what was the progress of the DFS. The DFS started in the root. The DFS visited all of the vertices in the first subtree, returned to the root, and then it went into a different subtree. And then only at this point, it visited the second vertex of the leftmost green edge in my example. Is this possible? Can this have happened? Well, no, it couldn't have happened like this, because as soon as I started DFS, and I finish processing this part of the graph, now I'm in this vertex, and there is one more edge I can traverse. So before I return from this vertex and continue exploring the rest of the graph, I have to go also along this edge, and this particular vertex cannot be in the second subtree. It would have to be already in the first subtree of my Dfs tree. So all of these green edges that are connecting vertices who are, in terms of metaphors as a family, these vertices are not each other's ancestors. So such an edge can never appear in a Dfs tree or in a graph where we run Dfs. So all of the remaining edges have to be edges between some of the vertices. So each of them has to go upwards in the tree, maybe all the way to the root like that. So for each of the remaining edges, once we have constructed the Dfs tree, we know that the lower and the higher endpoint of the edge must be, so the higher endpoint of the edge must be an ancestor of the lower endpoint of the edge in the graph. So this is the only possibility. In all other cases, the edge would be used earlier than that, and it would change the shape of the Dfs tree. And how can we use this observation to find the bridges? For each of the edges in the tree, we can ask the question, is this edge a bridge? So for example, is this edge a bridge? Let's take a look at what happens in the graph. So already in the Dfs tree, we know that what happens if we cut this edge is that the Dfs tree will fall apart into two subtrees. One of them is the one that contains the root, the other one is the one that doesn't contain the root. So is this edge a bridge? Well, no, it isn't. Why? Well, because we have this particular edge that still holds those two parts of our graph together. Even though we did cut this edge, it's still possible to get from this part of the graph to the rest of the graph, thanks to the edge that is leaving this particular subtree. Is this edge a bridge? The answer is yes. If you take a look at this particular subtree, there is absolutely no green edge that will be leaving this particular subtree. And therefore, if you are inside, the only way to leave is by using this particular edge of the Dfs tree, which you used to enter it. So this particular edge of the Dfs tree is a bridge because there is no other edge that can replace it. And that's the whole story. The green edges can never be bridges in a graph, because if you cut any of the green edges, the Dfs tree remains unchanged, and the Dfs tree holds the entire graph together. So only the black edges, only the Dfs tree edges can be bridges, and for each of them, this is the test we want to make. So if the entire subtree below this edge is only hanging on this edge and nothing else, the edge is a bridge. there are two more bridges or three more bridges in our graph. And this edge, and this edge. In each case, if we cut them, only one vertex will fall away from the graph. And what remains now is one final step. We need to be able to tell efficiently whether or not such an edge, such a green edge exists that will still hold everything together. So at this moment, we can already implement some kind of a bridge detection that will be reasonably efficient. So what you can do is run Dfs on the original graph. This will give you a Dfs tree of the original graph, and this gives you n-1 candidates for bridges. You could now test each of those candidates completely separately by removing the edge from the graph and checking whether it now fell apart into two connected components or not. But we can actually modify a single Dfs. So the single one Dfs that was already computing the Dfs tree will also compute some additional information that will allow us very easily to be able to tell which edges are and which edges aren't bridges. In order to do this, let's think about leaving a subtree. So suppose I'm in some vertex of the tree. This vertex is each vertex in the tree is determining one particular subtree that is rooted at this particular vertex. And now I'm asking the question, it is possible or not to leave this particular subtree by using one of the green edges? If it is possible, what does such a path look like? Well, I start here in the root of the subtree. I have to go downwards in order to reach one of the vertices in my subtree. And then from that vertex, I can use the green edge to leave the subtree. And a really clever way of computing such useful information about all of the vertices in our graph looks as follows. So as we are discovering vertices in our graph, we are going to give them new numbers. The vertices can already have their original IDs that are given as part of the input, or they can have even names or something like that. We are going to take a new color, let's say blue, and we are going to number the vertices in order in which they are visited by the Dfs. So you would have something like this. And as we are doing these computations, we will be also storing the following information. So for each vertex in the graph, we want to store the following information. If I'm allowed to go as many times as I want downwards using black edges, and then exactly once upwards using a green edge, what is the minimum blue number I'm able to reach by such a path? So I can take 0 or more steps down, then a single step up. What is the smallest number that is reachable? This information is computable directly during the Dfs. If I'm in a leaf, I cannot go down at all. So I'm just looking at the green edges going upwards from there. And I will see that for this 3, the answer is 1. And for this 4, the answer is 4. There are no green edges from the 4, so the smallest number I can reach is the vertex 4 itself. Now, when I'm finishing processing vertex 2, I can take a look at the values I already computed for its children. So what this is telling me is if I'm in the vertex number 2, I can go down here, and from there is a way of reaching the value 1. Or I can go down here, and from there is a way of reaching 4. There are no green edges from myself, so the best I can reach is still the 1. And for the 1, I will again compute the 1. For the 6, I see this an edge from 6 to 0, so it's 0. For the 7, it's 7. For the 5, it's 0. Now we go to the leaves on the right subtree. For the 10, you can go from 10 to 8, so this is 8. From 11, you go to 11 only. From the 12, you can get all the way to the root, so for the 12, it's 0. Now the 9 sees the options of going down and then to 8, or going down and then to 11, or going down and then to 0, so 0 is the best. The 13 can only go to 13, the 8 can go to 0, and the 0 can go to 0. And that's it. So in a single traversal of Dfs, in linear time in the size of the graph, we have computed the blue values, which are the numbers of vertices in the order in which they were discovered, and also the red values, which is for each vertex, the smallest number of a reachable vertex via a single green edge. And now the rest of the algorithm is trivial. Let's look at this vertex. Its blue value is 1, and its red value is equal to the blue value, it's 1. So what this is telling us, there is no way of reaching any of the vertices that are ancestors of the 1 and have smaller numbers because they were visited sooner than the 1. And this means that the edge going from 1 to its parent is a bridge. If we look at vertex 8, that had the vertex that had the blue value 8, its red value is 0, which is less than 8. So if you are in the subtree that has root 8, there is somewhere a way of going from one of the vertices in this subtree to vertex 0 that is outside of this subtree. And therefore, the edge from 8 to his parent is not a bridge. It can be circumvented by the other edge. So if both of the blue value is equal to the red value, the edge to the parent is a bridge. So we can see that this is the case also for the 7, for the 11, and for the 13. And in all other cases, the edge is not a bridge. In much the same way as you could determine the bridges, you can also detect the cut vertices in such a graph. And I'll leave it as an exercise, how to modify the algorithm. You want to compute slightly different thing, but not that different. So think about what exactly is the thing you are trying to check right now. What does it mean that a vertex is a cut vertex? And in the algorithm for cut vertices, don't forget about the special case, which is the root of the tree. When we had bridges, we only had n-1 candidates for a bridge, the edges of the Dfs tree. If we are looking for cut vertices, each and every one of the n vertices of the graph can be a cut vertex in general. Well, not all of them at the same time. But in particular, the root of the tree can also be a cut vertex, and this requires some special handling. But luckily, the handling is very easy. If you start Dfs in a vertex and you visit the entire graph already via the first edge you used, then the vertex is not a cut vertex. But if you visit only a part of the graph, you are forced to return to the vertex where you started, and then you have to continue via another edge to visit the rest of the graph. Then this means that the vertex is a cut vertex, and removing it will break apart the vertices that were visited before we returned and the rest of the graph. All right, then. So I hope that by now you already have some appreciation of Dfs and the magic things it can do for us. But we are still not done, and I will show you one more trick for our webinar that can be done with Dfs. And this will be a trick on trees, and it will show you that problems on arrays and problems on trees can essentially be solved via the same technique, many of these problems. So let's start with an array-based problem. There is a whole class of problems on arrays when we are doing some kinds of operations on contiguous segments of an array. So for example, one possible type of operations would be increment all of the values in this range by 7. Set all of the values in this range to the same value. Set all of the values in this range to the minimum to the current minimum of the range, and so on and so forth. And maybe there can be also queries. What is the current sum of this particular range? Maybe there can be point queries and point changes, change this particular value, determine this particular value, and so on. And essentially all such problems can be solved via the same technique. These are interval trees or segment trees or whatever you prefer to call them. My favorite name for this type of trees are tournament trees, because it's unambiguous. Everybody understands that what the tournament tree is intuitively, and it doesn't collide with other uses in other areas. So what you do is you build a perfect binary tree on top of the array. And now this tree has the property that each and every query in the array can be split into a logarithmic number of smaller intervals, such that each of those intervals is represented by a vertex of the tournament tree. So this particular vertex represents just itself. This vertex represents the range of 4 elements that are next to it. This vertex represents the range of those 2. And you can recompute the information stored in the nodes of the tournament tree. And you can also do updates if you want to set all of the values in this particular red interval to 7. Then you can just, in each of these 3 vertices, you can store the information that everything below me is now a 7. And then you do lazy propagation of those values whenever you have to. So there is a standard, this is a very standard tool that can be used to solve many, many different problems on arrays. And what I'm going to show you now is that this exact same tool can also be used to solve many problems on trees. What is this going to look like? So suppose we have a company, and in the company there is a boss, and the boss has some employees, and each of those employees has some employees that work for them directly, and maybe each of those, or some of those at least, have employees of their own, and so on. So there is a tree-like hierarchy in the company. And let's say each of the people in the company has salary, and now we want to modify those salaries efficiently. So we want to be able to do operations like, tell me what is the current salary of this particular person, give the end, or maybe one type of operations we would like to do is operations on entire subtrees of the tree. So for example, we can select this entire subtree. So say that take the branch of the company that is that has this particular employee as the boss. So everybody in this branch of the company should get a raise. They will get $100 more every month from now on. And now we would like to do operations like this on the tree efficiently. What's the problem with that? The problem is that trees can have very different shapes. The main reason why the segment tree or the tournament tree was efficient was because we forced it to be binary. So the depth of the tree was guaranteed to be logarithmic in the length of the array. And all of the operations on the tree therefore terminate very quickly. The depth of the recursion can be at most the depth of the tree. So if you have a tree that is nice and shallow, you can usually do many kinds of operations on the tree efficiently just by doing them in the very same fashion that you would with the tournament tree. But it's also possible to have a company with a structure maybe like this, or maybe like this. So each of those has a secretary that works just for them, but there is also a huge chain of people. And now if you want to process information about this entire subtree, then you cannot afford to traverse all the way down here. So if I ask you what is the salary of this person, you cannot afford to traverse the entire path from the director of the company all the way down to this poor employee somewhere on the bottom. simply because the length of the path can be linear if the tree has an ugly shape. So what can we do to prevent this, and how can we solve all kinds of operations on the tree efficiently? Well, you probably know the answer, even though you may not know how to do it yet, but you know the answer will be Dfs, which is what we are talking about today. So here's what we can do. We will do exactly the same thing we did with the Vertices algorithm. We will just do the blue numbering. For each vertex, you will give it a number as soon as we discover it, as soon as we start processing it. 0, 1, 2. Now this one is discovered 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And that's it. Because now we can make a very important observation. If you select any subtree of this tree, and by subtree I mean entire branch of the company, so you just select what is the root, and everybody that is below that particular person belongs into the subtree. So for each subtree of this form, the numbers the people in the subtree have to be contiguous. So they have to be a sequence of consecutive values. In this case, in my example, these are values 1 through 8. Why is this the case? Well, this is how Dfs operates. At some point, the Dfs entered this branch of the company. Then it visited everybody within the branch of the company. This is giving them the consecutive numbers. And then Dfs left and went elsewhere in the company. So for each branch of the company, we now know that the people in the branch have consecutive numbers. How can this help us? Well, we can transform the original problem on the tree into simply a problem on the array. If you imagine that now you have an array where the blue numbers are the indices into the array, and in the array you are storing the salary of each of those people, then each query about a branch of the company is now a query about the contiguous range in this particular array. And that's easy. This is something we can already do. We know how to do it. So simply by doing Dfs numbering of a tree, we can transform a problem on the tree into a problem on the particular array. Sometimes this is given a fancy name like a Euler Tour technique, but you don't need to know the fancy names. What is important are the concepts, understanding what is going on and why this particular thing works. And when we are talking about Euler tours, so this is the question of drawing a picture without lifting the pen from the paper. And without going along the same edge twice. This is essentially the problem that was at the birth of graph theory itself. This was in the town that was back then called Königsberg, now it's Kaliningrad, and Leonhard Euler encountered a problem that was a challenge to traverse each of the 7 bridges of Königsberg exactly once. And he was able to model this problem as a graph and show that such a thing is not possible. Nowadays, we already know what to look for. So drawing a graph, drawing a picture without lifting the pen and without going along each of the edges, along any of the edges twice, is called an Euler Tour of a graph. And formally what it means is we want a sequence of edges of the graphs that contains each of the edges exactly once, and each of the edges continues after the previous one. So wherever the previous one ended, the next one has to begin. And again, Dfs can easily be modified to actually construct such a tour whenever it exists in a given graph. I will not go into details because, yeah, webinar is already quite long, and we have seen a lot of different applications of DFS. So for this one, I will just leave it as a pointer that this is again something DFS can do, and there are tutorials available you can look into to see how you can do it. And yeah, let's slowly bring this webinar to a close, and I will show one last thing, and then I maybe, if you still have one or two questions, I can try answering them, and if not, then we'll be done for the day. So one last thing, one last trick we can do. Let me again start by drawing some kind of a tree. And this time we will focus on two separate events for each of the vertices. The first event will be the moment when we start processing the vertex. And the second event for each vertex will be the moment when we terminate its processing. So I will use a different color, let's say orange numbers for the later ones. And in this case, let's imagine that each of the events advances a time counter. So at time 0, we started processing the root of the tree. At time 1, we started here. At time 2, we started there. At time 3, we started with this particular vertex. At time 4, we finished processing that vertex. At time 5, we finished processing its parent. At time 6, we started processing this one. At time 7, we started processing its only son. Oh, sorry, its leftmost son. And then at time 8, we finished processing that one. 9 and 10 for this one. 11 and 12 for that one. At time 13, we are done with the vertex we started processing at time 6. At time 14, we are done with the entire left subtree of the root. And now we would continue into the right subtree in exactly the same fashion. So for each of the vertices of the tree, we now got two separate integers: the time when we started processing the vertex and the time when we finished processing the vertex. And now what you can do is you can imagine these two things for each of the vertices as an interval on the timeline. So this is the time as it flowed during the DFS. And this is the interval 114. And within the interval 114, we had the interval 2,5. And within the interval 2,5, we had the interval 3,4. And after the interval 2,5, we had another interval 6,13. And what we can see now is that for any two vertices in the tree, there are only two possibilities. Either their intervals are nested within each other, so one of them is strictly smaller than the other, and the smaller one is completely inside the bigger one. This is one possible case. Or the other possible case is they are disjoint, so one of them ends, and only afterwards the other one begins. And we can easily see that the first case corresponds to situations when the vertex with a smaller interval is a descendant of a vertex with a bigger interval. So you entered, so for example, with the 1, you entered the subtree, and then everybody that was visited while you were in the subtree, so between times 1 and 14, are the descendants of this particular vertex. And that's precisely the set of descendants of this particular vertex. Everybody else who is in different subtrees will be visited strictly later, or maybe strictly sooner if there are others. And everybody who is a descendant of this particular vertex will be visited between the moment when we started processing it and the moment when we finished processing it. So if we pre-compute this particular type of information, what it allows us to do is in constant time, we can now test whether one vertex is an ancestor of the other. And this is a very useful tool, for example, in efficient implementations of algorithms to find the least common ancestor of two vertices in a tree. You can use techniques like binary lifting to be able to compute, to be able to quickly jump many layers up the tree, and you can essentially use this then to binary search. So if you want to find the least common ancestor of vertices x and y, you can imagine that you have the path from y to the root of the tree. So yeah, let me draw it as a picture. It's always better to see it. So we have a large tree, and somewhere in the tree there is x, somewhere in the tree there is y, and there is a path from y to the root. And as you go along the path to the root, somewhere along the path there is the place where the path from x to the root and the path from y to the root meet. And this particular vertex z is the least common ancestor of x and y. This is the vertex we want to find. And the thing we just pre-computed gives us the option to essentially do binary search along the blue path, because on the blue path, you first have some vertices that are not ancestors of x, and then you have some vertices that are ancestors of x, and you are looking for the lowest of those that are also ancestors of x. So if you can jump along this path using steps that are powers of 2, for example, then you can efficiently find z in logarithmic time, regardless of the shape of the tree. All right, so I think that's it for today. Those were the topics I prepared to talk to you about. One other thing I would like to remind you about before we end is that we will soon be setting up an educational round in the Topcoder arena. We have selected 10 graph problems from past Topcoder competitions, usually several years old. So if you are rather new to Topcoder, you probably haven't seen and solved those problems, or maybe only 1 or 2 of them. And this round will then be available for 24 hours. I'm really not sure right now about registration, but please try to register for the round before the round starts. That's probably safer. I'm not sure whether it will be possible to register during the round. You can then solve those problems at any point during 24 hours. This is not rated. This is just for fun, just for educational purposes. So if you are willing to do some practice on graph problems, then we have a selection of those problems for you, and you can go to Topcoder Arena, and soon, maybe within an hour, there should be a contest set up for you. All right, so thank you for your attention. I'm really pleased you decided to spend your valuable time with me, listening to me. Hopefully I was able to tell you something interesting. I would be glad to hear feedback from you if you have any, and certainly we'll see each other later during one other webinar on some topic from algorithms. So if you have something special you are interested in, also let me know, and it might influence our choices of webinars in the future. All right, so I think that's it for me.